When splicing larger aluminum conductors, specifically 2/0 and up, there are several methods available, each with its own advantages and disadvantages. These methods can be broadly categorized into mechanical splices and electrical splices. Firstly, let's discuss mechanical splices. These include compression splices, split bolt splices, and bolted pressure splices. A compression splice utilizes a mechanical tool to apply pressure to the conductors, effectively creating a cold welt. A split bolt splice involves placing a split bolt over the conductors and tightening it, resulting in a mechanical connection. Bolted pressure splices use bolts to apply pressure between two conductors, establishing a secure connection. The advantages of mechanical splices are that they are generally quick and easy to install. They often do not require special tools or extensive training, and they are suitable for a variety of conductor sizes and shapes. However, mechanical splices also have disadvantages. They can degrade over time due to environmental factors, potentially leading to corrosion and increased resistance. This degradation can compromise the integrity of the connection and potentially lead to failures. The second type is electrical splices. These include CAD-weld splices, flash butt welding, and argon-shielded arc welding, also known as TIG welding. A CAD-weld splice is an exothermic welding process that creates a permanent molecular bond between the conductors. This process involves using a mold and a special welding compound to generate heat which fuses the conductors together. Flash butt welding is a method that uses an electric arc to fuse the conductors together. The conductors are brought into contact, and a high current is passed through them, creating an arc that melts the metal. Argon-shielded arc welding, or TIG welding, is a welding process that uses a shielding gas, typically argon, to protect the weld from contamination. This process provides a clean and precise weld, making it suitable for critical applications. The advantages of electrical splices are that they create a permanent and robust connection. They offer low resistance and high conductivity, ensuring efficient electrical flow. They also provide excellent protection against moisture and corrosion, enhancing the long-term reliability of the splice. However, electrical splices also have disadvantages. They typically require specialized tools and training, increasing the cost and complexity of the installation. They are also more time-consuming to install compared to mechanical splices, and they may not be suitable for all conductor sizes and shapes. When choosing the best method for splicing large aluminum conductors, several factors should be considered. These factors include the conductor size and type, the environmental conditions, the availability of tools and expertise, and the cost and time constraints. Conductor size and type are critical considerations. Mechanical splices are generally suitable for smaller conductors, typically up to 500 kcmil, where kcmil stands for thousands of circular mils, a unit of area used to measure the cross-sectional area of conductors. Electrical splices are often preferred for larger conductors, typically over 500 kcmil, as they provide a more robust and reliable connection for these larger sizes. Aluminum conductors require special splicing techniques due to their unique properties. Aluminum is more prone to oxidation than copper, and this oxidation can create a layer of high resistance on the surface of the conductor. Therefore, it is essential to use splicing methods and materials that are specifically designed for aluminum conductors to ensure a good electrical connection. Environmental conditions also play a significant role in selecting the appropriate splicing method. In environments with high moisture or corrosive elements, electrical splices are generally more resistant to degradation than mechanical splices. The permanent and robust nature of electrical splices provides better protection against these environmental factors, ensuring a long-lasting and reliable connection. The availability of tools and expertise is another important consideration. Mechanical splices are easier to install and require less specialized equipment compared to electrical splices. This can make them a more practical choice in situations where specialized tools or trained personnel are not readily available. However, it is essential to ensure that the mechanical splice is properly installed and tightened to achieve a good electrical connection. Cost and time constraints can also influence the choice of splicing method. Mechanical splices are generally less expensive and faster to install than electrical splices. This can make them an attractive option in situations where budget and time are limited. However, it is important to weigh the cost and time savings against the long-term reliability and performance of the splice. For critical applications where long-term reliability is essential, electrical splices such as CAD weld, flash butt welding, or TIG welding are often the preferred choice. These methods provide a permanent and robust connection that is highly resistant to moisture, corrosion, and other environmental factors. For less demanding applications or where costs and time constraints are a significant factor, mechanical splices can be acceptable, provided that they are properly installed and maintained. It is important to note that regardless of the splicing method used, proper preparation of the conductors is essential for a good electrical connection. This includes cleaning the conductors to remove any dirt, grease, or oxidation, and ensuring that the conductors are properly aligned and tightened. In addition, it is important to use splicing materials that are specifically designed for use with aluminum conductors. These materials typically include a corrosion inhibitor that helps to prevent oxidation and maintain a good electrical connection. Furthermore, all splicing work should be performed in accordance with applicable electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for splicing conductors, including the type of splicing methods and materials that are permitted for different applications. It is essential to consult the NEC and other relevant standards to ensure that all splicing work is performed safely and in compliance with applicable regulations. The NEC has various tables and articles that are useful when dealing with conductor splicing. For example, NEC Table 310.16 provides opacity ratings for various conductor sizes and insulation types, which can be helpful in determining the appropriate conductor size for a particular application. NEC Section 110.14 covers the requirements for electrical connections, including splicing. This section specifies that all connections must be made in a way that ensures a good electrical contact and prevents overheating. The section also addresses the use of connectors and splicing devices, requiring that they be listed for the specific application. NEC Article 300 covers wiring methods and materials, including requirements for conductor splices and terminations. This article provides guidance on the proper installation of conductors, including the use of appropriate connectors and splicing techniques. Furthermore, it is important to consider the specific requirements of the local electrical code, as these may vary from the NEC in some cases. Local codes may have additional requirements or restrictions on the type of splicing methods and materials that are permitted. When selecting a splicing method, it is also important to consider the voltage and current rating of the conductors. The splicing method must be capable of handling the voltage and current that the conductors will be carrying. Using a splicing method that is not rated for the voltage and current can lead to overheating, insulation failure, and even electrical fires. In addition to the splicing method itself, the quality of the splicing materials is also critical. Using substandard or counterfeit splicing materials can compromise the integrity of the connection and potentially lead to failures. It is essential to use splicing materials that are listed by a recognized testing laboratory, such as Underwriters Laboratories, or UL, and that are specifically designed for the application. UL listing indicates that the splicing materials have been tested and found to meet applicable safety standards. When installing splices, it is important to follow the manufacturer's instructions carefully. Improper installation can compromise the integrity of the connection and potentially lead to failures. The manufacturer's instructions will typically provide detailed guidance on the proper preparation of the conductors, the correct installation procedure, and the recommended torque values for tightening connectors. In addition to following the manufacturer's instructions, it is also important to use the proper tools for the job. Using the wrong tools can damage the conductors of the splicing materials, leading to a poor electrical connection. For example, when tightening connectors, it is important to use a torque wrench to ensure that the connectors are tightened to the correct torque value. Over-tightening connectors can damage the conductors, while under-tightening connectors can lead to a loose connection and increased resistance. After installing a splice, it is important to inspect it carefully to ensure that it is properly installed and that there are no signs of damage. The splice should be visually inspected for any cracks, breaks, or other signs of damage. The conductors should be securely connected, and the connectors should be properly tightened. In addition to visual inspection, it is also recommended to perform electrical testing on the splice to verify that it is functioning properly. This testing can include measuring the resistance of the splice to ensure that it is within acceptable limits, and performing a voltage drop test to ensure that there is no excessive voltage drop across the splice. If any problems are detected during the inspection or testing, the splice should be repaired or replaced immediately. Maintaining electrical splices is also important for ensuring their long-term reliability. Splices should be periodically inspected for any signs of corrosion, damage, or loose connections. If any problems are detected, the splice should be repaired or replaced promptly. In addition, it is important to keep the splices clean and free from dirt, grease, and other contaminants. Cleaning the splices can help to prevent corrosion and maintain a good electrical connection. In summary, splicing larger aluminum conductors requires careful consideration of several factors, including the conductor size and type, the environmental conditions, the availability of tools and expertise, and the cost and time constraints. Both mechanical and electrical splices have their advantages and disadvantages, and the best choice depends on the specific application. Regardless of the splicing method used, proper preparation of the conductors, the use of high-quality splicing materials, and careful installation are essential for ensuring a safe and reliable electrical connection. Always follow the manufacturer's instructions and comply with applicable electrical codes and standards.